This is a demonstration of OpenTLDR for the 2024 LAS Symposium. It includes presentations, followed by screen captures and narrative demonstrations. It covers OpenTLDR's various user interfaces and use of the analytic playground for end-to-end functionality. OpenTLDR was developed by Rockfish Research under contract with the Laboratory for Analytic Sciences at North Carolina State University. We appreciate and acknowledge the Department of Defense for their support that makes this research possible. My name is Chris Argenta, and I will be guiding you through this demonstration. You can find me and a team of collaborators at our poster display. We welcome any questions and discussions. This is an introduction to OpenTLDR, a software framework that enables researchers to build systems that generate TLDRs. Researchers can use our modular framework to explore new ways of doing things and evaluate the results in an end-to-end working system. When we say TLDR, we understand this to be a playfully ambiguous fusion of two concepts. First, the abbreviation for too long didn't read, and the term tailored daily report. For example, consider the President's Daily Briefing, which is a shortened overview of the things the President needs to know to keep up with the latest events around the world. We generalize this to a recurring short report that updates any knowledge worker with the most relevant information that they need to know. The reason these concepts come up together now is that knowledge workers are finding it difficult to keep up with and avoid being overwhelmed by the vast tornado of information blowing around the internet at any given day. There is more information out there than we can read, and it changes continuously and is in many different forms. All the V's of big data come into play here. We often cannot know a priori what is true, and different information can sometimes be useful for different purposes. If keeping up with the latest information is critical to your job, you can easily spend considerable time each morning updating your awareness of everything that's changed since the day before. A TLDR system sits between a knowledge worker and this tornado of information, attempting to optimize the flow of information and balance two key goals. The first goal is to maximize the user's awareness of relevant information. Relevance is the quality of being useful for a given purpose, so a TLDR system needs to tailor the selection and presentation of information for that purpose. The second goal is to minimize the demands on a user's attention. Cognitive science suggests that attention is a limited resource, so we want to reduce the amount of less relevant content the user is required to process. The key to a good TLDR is in the tailoring of information to achieve these two goals. OpenTLDR provides a framework and working end-to-end system for producing TLDRs that address these goals. From the knowledge worker's perspective, there are three parts to this process. First, each TLDR is tailored to a specific information request. In the default OpenTLDR workflow, a request is a text-based statement about the user's interest. Creating a request that adequately captures what is relevant can be challenging. If the request is too broad, the resulting TLDR will include content that might not actually be useful, wasting the user's attention. If the request is too narrow, the resulting TLDR may not include some information that is relevant, resulting in a loss of situational awareness. For this reason, some research is focused on helping the users create good requests. For example, Digger is a user interface that enables the user to interactively create requests and control the process of producing a TLDR. Some of our TechInt research allows users to form requests by providing examples of relevant publications. A user can create multiple requests to encapsulate different topics that interest them. By default, the system will generate a separate TLDR report tailored to each request. Tailoring to a request is different than modeling a user's preferences, because what I liked yesterday doesn't always match the mission that I'm working on today. Next, each day, OpenTLDR wakes up early, starts its automated workflow. It collects all the latest information from a wide range of sources, parses through the content using natural language processing, automatically organizes and connects new content into its knowledge graph, and determines which information will be relevant for which requests. It then tailors down the relevant content into a TLDR report. By the time you roll out of bed, commute to the office, and pour your coffee, OpenTLDR has a daily report already waiting for you. In this completely automated information triage process, the system has filtered the tornado of information to just the information it determines will be relevant with respect to your request. Finally, the user performs the second pass of information triage. An OpenTLDR daily report prioritizes and summarizes each article to specifically tailor it to your request. So when you read the report, you are only focusing on what should be relevant and why it should be relevant. You then make the decision, do I want to invest more of my attention on this article? If the answer is yes, you can click through to the source. If the answer is no, you simply move on. Since a user can have multiple requests and reports can be shared with teams, all the relevant information can be easily encapsulated within the context of a specific part of your job. If you want to keep your international news separate from your interest in electric vehicles, no problem. And you don't have to worry about that baby panda article that you read finding its way into your research about semiconductors. All of the artificial intelligence behind the OpenTLDR workflow is geared towards balancing the user's attention with the value of the information provided. This is fundamentally different from systems that attempt to maximize the time you spend on a specific site or guessing what you might like based on what you previously viewed. It might help to think of the workflow of OpenTLDR as a machine that takes in three types of information and produces a new type of information. The inputs are active data, which consists of all the source articles, for example, the text content of news articles from an RSS feed. We are actively expanding the range of formats that this can include. There's a large volume of these that pour into the system each day, and this is why your TLDR report can change each day. Information requests, which are a user's expression of their interests. This can change over time if the user deliberately does so. The basic representation of this is in English text and natural language, but we are working on versions that use articles and papers as examples. So, for example, show me things that are similar to things that I already have. And finally, reference data. This is a knowledge graph that provides the context by which things are related. This ranges from the relationships, such as an organization chart, to ontologies of concepts, but even something as simple as a list of names of people of interest helps to layer curated enterprise knowledge into the process in a way that generic models can't do. Each entry in the resulting TLDR reflects a mixture of these information sources. The TLDR summarizes the active data with respect to the user's request and given the context provided by the reference knowledge, and this is the essence of the tailoring process. The OpenTLDR Playground is a functional open source system that generates TLDRs. It was designed to make it fast and easy for researchers to easily integrate their own research and evaluate the results in an end-to-end manner. Researchers can use our module framework to explore new ways to do things and evaluate the results in an end-to-end working system. The term playground here refers to a set of analytic components written as Python notebooks that interface through the OpenTLDR APIs. We separate the core infrastructure of OpenTLDR, shown here in blue, from the modular components that we expect the researchers to modify, shown here in gray. The components are implemented as Python notebooks, which many researchers are already familiar with for prototyping and documenting. While you can run each notebook manually for development and testing, the OpenTLDR framework includes a workflow component that parameterizes and executes these components in order automatically. The components in the default workflow have been selected to perform end-to-end, meaning each time you run the workflow, it starts with a clean knowledge graph, performs all the analytic steps in order, and ends by running the evaluations. When you first download the OpenTLDR Playground, we recommend running the workflow end-to-end with the out-of-the-box settings to verify that you've set up your environment correctly. You can then easily walk through this workflow and understand what is happening in each component and how they are interacting through the framework with each other. However, the point of a playground is not simply to run the configuration out of the box, but to integrate your own research and see how it performs in an end-to-end system. For example, if you perform research with the recommender models, you may want to see how your model compares. You can start by looking at how the baseline recommend component interfaces to the framework. Then, by simply swapping out your implementation for theirs, you can immediately have the benefit of a working prototype. However, the benefits don't end there, because by running within the playground, you can leverage the other components, user interface, and evaluation datasets. This results in quickly getting to the point of understanding how your changes affect the overall performance of the system. For students, this provides a way to experiment with new approaches and rapidly get the information you need to publish a paper and perhaps demonstrate it at an OpenTLDR workshop. As we all know, a playground was more fun with your friends, so integrating their components with yours is also easy. One of the key reasons that this plug-and-play modularity works is that there is a consistent knowledge graph schema being incrementally built up over the steps of the workflow. The schema is shown here. No matter how large or complex the knowledge graph becomes, the nodes and types shown here and the relationships between them are maintained. While independent researchers are free to create their own nodes and relationships, these are objects directly supported by the OpenTLDR Knowledge Graph API. For example, in our TechInt work, we're extending this schema to include detailed parts of technical documents. To ensure these enhancements interoperate, we always tie them back to one of these objects. The default workflow in the playground consists of 7 stages, or steps, that are implemented as independent Python notebooks. This makes modifying them easy. The workflow starts by wiping the knowledge graph clean, incrementally building up the data and workflow products, and finally running the evaluation steps. If you're working with the same data set that comes with the OpenTLDR repository, it already includes all of the reference data, requests, content, and evaluation keys you need to produce the knowledge graphs and results we'll walk through here. For running experiments, we always want to start with a clean slate. So by default, the initializing step clears all the data from the knowledge graph. It then imports the reference data. The sample reference data will look like the graph on the right when viewed directly through the Neo4j tools. Reference data represents the curated enterprise knowledge that provides the context for understanding and relating objects found in the active data. The ingest step is responsible for loading content into the knowledge graph. This content can come from a sample data repository, as shown here, or from other data repositories such as S3 buckets. First, it creates the content node for each article and connects it to the node for the source of these articles. Content nodes are shown in green. For each content node, we run named entity recognition, keyword detection, and potentially other analytics to parse the content text. Here, the named entities are shown in gray, connected to the content nodes in which they were identified. To support repeatable experiments in the playground, we had a special step to inject canned users and user requests, shown here in blue. Since a TLDR is tailored based on these requests, consistently using the requests for which the expected answers have been curated is important. Like content node, named entities and keywords are also extracted and connected to the requests, shown here in gray. At this stage, there are 3 distinct networks in the graph. The connect step is where we establish relationships between the reference data and the entities extracted from the content and requests. This is a form of entity resolution, where we have entities from 3 different sources and we want to identify if they refer to the same thing. The default algorithm uses a pairwise cosine similarity to find the best match above a threshold parameter. If there are entities that appear multiple times, we will also hypothesize new reference data to connect them, but it tracks which are hypothesized and which are from curated knowledge. The next step of the process reviews the connectivity between the requests and content, which always includes a path through reference data. It scores the combination of these paths. When the score is above a threshold parameter, it creates a recommendation, shown in red, which links the request to the content more directly and with a scored relevance. The summarize step creates tailored summaries of the content that was recommended. In the default case, there are abstractive summaries from an LLM. In the graph, these are purple nodes. The prompt for the LLM includes the text of the request, the text of the content to summarize, and the set of statements extracted from the paths between the content and the request. This tailors the abstractive summary to what is being asked and the curated reference knowledge about it. This is an implementation of Retrieval Augmented Generation, or RAG, more specifically GraphRag. But it is uniquely designed to tailor a summary to be the most relevant to the request given this background knowledge, not to include random data from other material. To say this differently, any combination of requests and tailored article, a tailored summary includes relevant context about why or what specifically about these might be relevant. As a result, hallucinations are reduced and the focus of the summary is more targeted to the relevant material. Each day, the recommended articles and summaries are gathered for each request. A TLDR node, shown as large black nodes, are created, and specific TLDR entries, smaller black nodes, are created and linked to those. In the default notebook, one entry is created for each recommended content article. These are shown as smaller black nodes. The final step in the workflow for the OpenTLDR playground runs a set of evaluation calculations. These require that a known correct answer be provided. This is done by importing eval key nodes, displayed here as white nodes. The evaluation key identifies the expected recommendation and summary results for pairs of requests and content. There are many metrics that can and have been implemented here and within other steps of the workflow. The default playground prioritizes evaluations that are important for the end-to-end results because this allows us to see the joint effects of changes to different pieces of the process. Here's a list of the default metrics computed. These all work with the sample data sets. Other metrics have been implemented, as well as interfaces to reporting tools like MLflow for parametric studies. These three novel metrics on the right, selection, are how close we get to a recommendation, focus, how well the summary is tailored to the request, and reduction, which is how much smaller the summary is than the original content. If these scores are high, the system will be doing a better job of triaging the content and tailoring it to what a user should find relevant. As we'll show here, running the playground on a sample dataset only takes a few minutes. Running it manually helps you get a sense of what it's doing at each step and allows you to explore the knowledge graph as it is being built up. Okay, to show you how quick the playground runs, we'll start with step 0, which initializes the database and loads in the reference data information. So here we're deleting, and there we are loading in the reference data, which happens to be a Cipher file. In the ingestion stage, we connect to a data repository and load the articles. And for each article, we pull out different named entities using the SPACY algorithm. And from there, we pull out named entities and put them into the knowledge graph, which is shown here. The next step mocks up a user interface, adds the request information for multiple people, and does the similar SPACY processing to get entities from that. The connection process takes the entities discovered from both the active news article data as well as the request. For each of those, it attempts to link and identify entities named in one with how similar they are to entities named in other ones, and particularly with reference data. First step, it tries to link everything to reference data, and the next step is it tries to discover things that are not listed in reference data but referenced in multiple articles. This is particularly important for news articles in which you might not have all the reference data. In the recommend step, it looks through the graph of connectivity and tries to find paths between the request and the articles themselves, and those that score highly in this algorithm are then recommended. These kind of show the recommendations. Summarize step uses a local running LLM based on GPT4All and does an abstractive summary. You can see here it's connecting. It should be using the GPU already in my device here, and runs the summarization. Go down. First thing it does is it pulls out information about the graph and how these things are connected, and it includes that in the prompt. So this has a specialized prompt that includes the article that needs to be summarized, the request that it's summarizing it for, as well as the path information through the reference data for what's relevant for context. And for each of these, it runs a summary, and this kind of shows what the prompt was and what the summary comes out as. And you can see it runs fairly quickly, although this is the longest running process. does this for each of the recommendations, and each of these are going to be put into the TLDR. The produce step assembles the TLDR by looking at those summaries and recommendations and assembling them into a structure that represents the TLDR. There's one TLDR for each day for each request. And then the evaluation stage, if you have evaluation key data, will run through, compare what the keys say, and the keys are basically the known right answer, with what your TLDR produced, and compute some metrics on that. So this is the metrics that it's computing right now. First, just in terms of which things got recommended, for which articles it gives it a score, and then we also have, so you get the precision, accuracy, recall, and F1 scores based on that. We've also added 3 additional metrics which are focused on how tailored the TLDR is. And so this is selection, which is how close were my recommendations to what ideally we would have recommended. Focus is how much is the content of the TLDR summary entry similar to what the key thought it should be, and reduction is how much we reduce the content from the original article down to the summary. For the fastest hands-free execution, we can also run the playground automatically as well. This notebook can easily be modified to change the process as needed to support new research steps. Able to run all of the notebooks separately, you have the ability to run them all one after another automatically in a headless mode using the workflow. And so here's a notebook that basically defines the workflow as a data structure and then runs it. I'm going to go ahead and kick that off so you can see what that looks like. Basically, it's walking through each of the steps individually in the TLDR that we just did, and it's running them headlessly. As these are running, it is creating copies of the notebooks up here that it can use to debug, basically. So if you have an issue, then the actual running is recorded here in a read-only version, so you can go back and see what's going on. And that's all specified here in the workflow object, which includes the order of the steps in the run and any parameters that you need to pass in. These parameters are used in the notebook itself. You can see there's a parameter block specified here, parameters, and these can be overridden by the workflow, which allows you to basically change the behavior of the notebooks without actually changing the notebooks themselves. Again, the summarization takes the longest and uses the most CPU power. But in the end, you'll get the same results. Including the evaluation. This presentation provides an overview and demonstration of user interfaces for OpenTLDR. OpenTLDR provides a default user interface that was designed to provide researchers with a baseline working example and API that works well within the framework. However, the intent is for researchers to leverage the modularity of the framework to replace our module with their own implementations. There are 3 things that any TLDR interface will want to do. The first is to enable users to create and manage their requests. The default implementation can accomplish this with a few simple text entries. In a live system, the TLDR workflow runs every day and ingests new data and produces new TLDR reports. So the second thing the user interface must do is provide access to these reports. The default implementation manages reports by day under each request. The last thing is collecting user interface feedback. Each TLDR report provides an appropriate set of TLDR entries. In the default interface, these are simply a bulleted list that has been instrumented to provide feedback on user interactions. For each entry, there is a title of the original content, a tailored summary, the relevance score, and a link to the original article. The article here is unchanged and at the source's website, but the process by which it's presented to the user has already triaged this article twice. resulting in it being a higher likelihood that this article will be relevant to the specific purposes indicated in the user's request. Underlying the user interface are a series of RESTful web services that any implementation of the user interface can easily connect to the framework and knowledge graph. The following recorded demonstration shows the OpenTLDR default user interface. For demonstration purposes, we incorporate the same sample dataset that is provided in the open source repository. This sample dataset consists of a series of fictional news stories that follow characters named Alice, Bob, and Charlie in a story about peanut butter and jelly sandwiches at the first bank. While the story is silly, the dataset has been designed and curated to incorporate realistic features of a series of reports about an evolving news story, as well as an automatic scoring mechanism for TLDRs. Sample user interface starts with a screen that allows users to view the current requests in the system, as well as add additional requests. If you click on one of the TLDRs, you'll see the news article that's summarized, the summarized version of it, the relevance that it was given, and a link to the source file. So if I click there, it pulls me up the actual source. In this case, it's just a text file. In addition, if I go and I say, okay, this is not the relevance I would have given this, or this is not the summary I would have given it, maybe I thought it was a little better, I can click on that, and that will send feedback back to the system that gets recorded in the knowledge graph. That way, over time, you can develop a database of users' interest. Since it's built on the FAST API, you can go in and look at the API specifications, which include all of the REST interfaces, as well as the objects that get passed back and forth. And you can go in and you can click on one of these and actually run the API call and see all the details about what gets returned. The REST interface, it's all JSON based. And so this should make it pretty easy to add new capability onto the API. This next demonstration showcases a specific user interface that was built on top of OpenTLDR. Digger is a prototype user interface that we developed in collaboration with William Elm of RCS as part of the 2024 Summer Conference on Applied Data Science, or SCADS. It provides an excellent example of how quickly concepts can be implemented on top of OpenTLDR's modular framework. It went from a hallway discussion to a whiteboard sketch discussed with visiting analysts to an integrated end-to-end working prototype in about a week. This is a demonstration of the Digger interface. The Digger interface is built on top of OpenTLDR, so all of the capability that we have in OpenTLDR is available through an API to the Digger interface, and the Digger interface both can be called from and used to produce TLDRs that go into there. So we're going to start here to answer a question that a lot of analysts had was, how do I know if I have a good analytic request? And so we're going to start up here on the left-hand side, and we're going to type in a request. In this case, we're going to pretend that we are a bank security guard and at the first bank, and we're going to ask questions about, so tell me about suspicious activity near the first bank. So OpenTLDR in this particular version is highly sensitive to named entities, so it'll focus on those. And so we want to make sure we include some of those. Some of the newer versions use keywords and other things as well. Talk about that later. We then press the dig button, and you'll see here the relevance of articles. And so this is the articles over time. This is the most recent going to the oldest, least relevant going to the most relevant. And you'll see some of these popped up to the top, indicating that some have very high relevance to our request. And so they are, in theory, about things near the first bank. And so let's start here by selecting some that are on the very highest relevance. And we select those, and they'll show up here in the list. We can sort this list, but they're all the same score right now. Up here at the top, we're producing an abstractive summary that takes the selected 5 articles, tells you a little bit about them with respect to what they have in common and how they differ a little bit. And that is based and tailored on the requests that you've put into here. And so your request, the articles, summaries of the articles are used as a group here. If we select a particular article from this list, we go over to the right-hand side, and it is producing a tailored summary. And this tailored summary includes 3 things. It includes the actual article content, the information about your request, as well as some augmentation from a knowledge graph. In this particular case, we see our request was first security, In that request, we used First Bank. We have reference knowledge in the knowledge graph that knows about First Bank. First Bank was also detected in story 1. And so this gives you a summary here that's been tailored to all those pieces of information. And if we view the content of that, we can see the actual content of the story. So this is just a fictitious story that we created for demonstration purposes. If this article was very useful to us, we might choose to cite it in the TLDR. And I'll talk about how that works in a little bit. We can go on to the next article and see, okay, this one also has a similar pattern of, first security is our request, the first bank is in our reference knowledge, and again, the first bank called in there. All of these, in fact, will have a similar pattern because they were highly relevant. If we look at some of the ones that were slightly less relevant, we'll see a little bit different pattern. And so in these particular cases, I'm going to select these two, and I can see information about how they're in common and what they have in common and what they have that's different, as well as when I select one of these, I now see a different set of knowledge that has been found in the knowledge graph. And this says that the first bank was mentioned, and I know about First Bank. I also know, as part of my reference knowledge, that First Bank is located on First Avenue, and First Avenue happens to be mentioned in this story. So if we look through this particular summary that's been tailored with that information, we'll see things like it pulling in information about the location here between First Bank and First Avenue. If I look at the source information for that one, you'll see indeed we mentioned First Avenue here, but nowhere in here do we see anything about First Bank. I specifically asked about First Bank, so the only place that information comes into play is because I have knowledge that referentially indicates that First Bank is located on First Avenue. And that's, I'm going to mark as also interesting. Now, let's suppose I want to extend out my request and say, okay, I'm interested in First Bank and a character that happens to be in our story named Bob Bobert. So now I have two different named entities in my graph, and so the relevance gets adjusted with respect to both of those. If I look at some of the more highly relevant ones, I get a summary about that. And when I click on it, you'll see that there's a relatively direct connection between the things that I asked about and the things that I'm told about. So in this particular case, I asked for security. From that, we recognize the name Bob Bobert. Bob Bobert is in our reference data, so we have linked him here to the story, as well as we've referenced First Bank. We've indicated that, but we now know Alice Allsorts, and so Alice happens to work at First Bank and be a manager there. And we might know that from some of the different stories, but this particular story I don't believe does. So that information is coming in from essentially org chart information in the knowledge graph. And so here's the actual article. And we can see that talk about Alice, talk about Bob, but nothing about the fact that Alice works at First Bank. So actually nothing in this article mentions First Bank or the location of First Bank, but because we have organizational information in our reference data that says Alice works for First Bank, we can make that connection. And let's go ahead and cite that one in there as well. As we start looking at some of the ones that are slightly lower relevance, we'll start to get some in here that are probably mistakes. Like, for example, Hurricane Beryl probably has nothing to do with First Bank or Bob Bobert, which are fictional. But if we start selecting and looking at how these are connected, again, we get a summarization about all of them, including in this particular case that this Hurricane Beryl shows up, and that's odd. See, okay, here's my request. I don't have a link for Bob Bobert. I do have a link for First Bank. First Bank took me all the way to story 4. I select the one that here is about the hurricane in the Caribbean. Wait a second for the thing. I'm going to see, okay, I have First Bank again. That didn't connect. I have a Bob Bobert. Bob Bobert's in my reference data, and he's been connected, in this case erroneously, with a person named Ralph. And so there happens to be a person mentioned in this that's by the name of Ralph, and it thought that was a connection. Now, that connection is actually likely to be a low probability or a low scoring connection, but still it's pulled into the query here. So let's go look at some of the ones that are particularly low ranking because they're very informative about how the graph pulls this information in. So here I have my request for security. I have a character named Bob Bobert that I've asked about in that request. I've linked that to my reference data. I happen to know that Bob Bobert works at Deadwood Arcade because that's in the reference data. The Deadwood Arcade is located on 3rd Boulevard. The New News Today Daily newspaper is also located on 3rd Boulevard, and a person works there by the name of Charles Chuckles, and Charles Chuckles is mentioned in this particular article. So if I go and pull the source up for that article, the only information here that links these really at all is this path through the reference data about Charles Chuckles. So there's nothing about First Bank, nothing about Bob Boberg, which is why this is a very low relevance, but it does keep that connection intact. Okay, so this is how the Digger user interface works. I'm going to show a little bit here about how we interface this with the rest of OpenTLDR. So if I go and select, this is the standard dashboard for OpenTLDR, and you can see that now I have a request that was generated today. I could go back into the Digger interface. I could also look at the timeline view. I'm going to select here, and here are the 2 stories that I cited. I can go and read those stories there. So because I selected 2, they became my TLDR for today. This is based on that. And that request that I produced is also part of the system now, so going forward it will automatically be picked up, and the automatic processing of OpenTLDR will give me future information about that. Similarly, I can pull that up in the timeline view and see both those articles in the timeline. This concludes the demonstration of OpenTLDR for the 2024 LAS Symposium. I want to thank everyone for their time, and thank you to the collaborators as well as to the sponsor organization.